Hey guys, this is Jonathan Gardner. Welcome back. We're doing Sergey Lang's mathematics, and this time we're covering real numbers, positivity, right? And we'll talk about what it means to have positive numbers and what the properties of this are. So, if we take a look at the real number line, okay, so it goes off infinity in both directions. We can choose an arbitrary point to be 0. We notice that there is, on this side, all the numbers are positive. And on this side, all the numbers are negative, right? And of course, we also have 0 that kind of, he's the guy in between. So we say positive, A is positive means that A is greater than 0, okay? Let's talk about some properties of positive numbers. First, we have the property, he's called it pos1. And pos1 says if A and B are positive, then A times B and A plus B are positive. A times B and A plus B are positive. Okay? And what that means is you can't leave this side of the number line by multiplication or addition with other numbers on this side of the number line. You're going to stay on that side of the number line. All right? Okay, positive 2. This theorem says that if A is real, then either A is positive, okay, or A is 0, or minus A is positive. Only one can be true. Okay? And we're going to see other theorems in the future of this book where we go and have these kind of dichotomies, or I guess it's trichotomy, right? Because we're cutting it into 3. If a number is not positive and not 0, then we say that this number is negative. So negative, let's write it over here. A is negative if A is less than 0. So it's not positive and it's not 0. Okay? All right? So what this is saying here is if A is negative, then minus A is positive. That shouldn't be too big of a surprise. All right? So we could use a simple proof to prove that 1 is positive. So let's do that right now. How would we do that? Well, we can take, a very simple proof to prove that 1 is positive. So by pos2, we know that either 1 or negative 1 is positive. So is 1 positive? So we know either 1 is positive or minus 1 is positive. Because we know that 1 is not 0 and minus 1 is not 0 as well. So if 1 or minus 1 is positive, then one of these will satisfy this condition up here. The multiplying by itself will give a positive and adding to itself will give a positive. Okay? Now we know that minus 1 times minus 1 is equal to 1, so that's positive. So according to the first part of pos1, minus 1 could be positive. But according to the second one, when we add minus 1 and we add minus 1 together, I'll just put parentheses around it this way, that is equal to minus 2. It is not positive. Okay? Therefore, minus 1 is not positive. Why? Because it flips from one side of the number line to the other. So 1 is positive. Okay? That was the options. All right, and the other way you could have done it is you could have noticed here that the signs flipped. Okay, if you're multiplying the number by itself and the sign flips, then it's not positive. Okay, all right, we conclude that 1 plus 1 is positive, 2 plus 1 is positive, and so forth. Thus, our calling 1, 2, 3, and so on, the positive integers, is compatible with the rules of positive 1 and positive 2, but notice that minus 1, minus 2, minus 3, etc. are not. Okay. All right, other basic properties of positivity, easily proved and they're left as exercises. Exercises 1, 2, and 3. So these are the other ones that are exercises for you. All right, so we have, if, let me get this marker in my hand, A is positive and B is negative, I'm sorry, then AB is negative. Another rule, if A is negative and B is negative, then AB is positive. Two more rules. If A is positive, then A to the minus 1, which is equal to 1 over A, is also positive. And the last one, if A is negative, then A to the minus 1, which is equal to 1 over A, is negative. All right? So we're not going to prove these, but they are homework assignments, and I do want you to try to prove these theorems, these conclusions, using only pos 1 and pos 2, and the basic rules of multiplication and stuff like that. Okay? One of the properties of real numbers, which we assume without proof, is that every positive real number has a square root. That says, let me draw a line here. If A is greater than 0, it's positive, then there exists a number B such that B squared is equal to A. Okay? So that means there are square roots and there are cubed roots. No, there are square roots, okay? Every positive real number has a square root, okay? Theorem 4, section 5 of chapter 1. We see that a number whose square root 2 is irrational, but it exists as a real number, okay? So B, such that B squared equals 2, is not rational. Remember we proved that? But it is real. So it's a real number. And I begin by real. Don't get hung up on the word. It doesn't mean that it's like physical and tangible. It means that it's part of the set of these real numbers. All right. It is reasonable to ask right away how many numbers there are whose squares are equal to a given positive number. So we said there exists a number. How many are there? Is it 1, 2, or 3? All right. Let's answer it. And the answer is there are precisely 2 such numbers. 2 such numbers. Okay? Not 3, not 1, there are 2 such numbers. Okay? One is positive, and the other is, you guessed it, negative. Let's see why this is. Okay, so new piece of paper. Let's see why this is. So we're going to start with this equation. So we say x squared is equal to 2. Okay, now we can say x squared minus b squared is equal to 0. Thus we have x plus b and x minus b multiplied together, and that has to equal 0. All right, so that means either one or the other has to be 0. Because if something's going to equal 0, then one or the other is 0. Or maybe they're both 0. Who knows? Let's find out. So let's say if x plus b is equal to 0. Then what does that say? X is equal to minus b. Okay? But if x minus b is equal to 0, then that means x is equal to positive b. Or just b. Okay? Okay? Now in this case, we had x squared equals 2, which is the same as x squared minus 2 equals 0. So we have b squared is equal to 2. b squared is equal to 2 as well. So x squared is equal to 2 and b squared is equal to 2, right? So that says that x has to be minus b or x has to be plus b. So we have 2 possible solutions. We have minus b squared, which is just minus b times minus b, which is b squared. And we also have b squared is equal to b squared, obviously. So thus we have proved our assertion. There are two numbers, and they're exactly the opposite of each other. Okay. All right, hopefully that you were able to see that whole proof. Now, here is something that we're going to call, it's a rule in algebra. And this is actually a rule that I didn't discover, or I didn't really recognize until much later. Okay, I didn't take algebra in college. I took it in like junior high school. So I didn't really understand the importance of this. Okay, when we write the square root of 2, this is positive. Okay? Square roots are always positive. Okay? Therefore, if you have x squared is equal to 2, then x can equal positive square root of 2, or x can equal negative square root of 2. Those are two possible answers to this equation here. They both work. But when we write square root of 2, we mean the positive. Okay? So the general rule is anytime you have the square root of a, that is always equal, greater than or equal to 0. So we write square root of a is greater than or equal to 0. It's positive. Okay? And it's unique. There is no negative number that is the square root of a. By definition, we're just choosing to be it that way. So a better way to write this is we write x is equal to plus or minus the square root of 2. We just use this plus or minus symbol, which means it can be positive or negative. And this is, in fact, if you're wondering where positrons, which is like the negative electrons, where they come from this particular property in algebra. Okay? When you do the math, you work it down until you get some equation that says something squared is equal to something, and you take the square root. You have to take the positive and the negative roots. All right. Another way of putting this, he says if x and y are numbers, real numbers, such that, I'll just write st, because this is an often used phrase, x squared is equal to y squared, then x can equal y, or x can equal minus y. So we just write x equals plus or minus y. Okay? So when you have two things that are squared equal each other, then either they're the same sign or they're opposite signs. Okay? Moving right along. Let's say we had the square root of x squared. So we take some number and we square it, and then we take the square root of that. Know that this has to be greater than or equal to 0, right? Okay. Like for instance, let's take we took the square root of minus 3 and we squared that. Well, that would be the square root of 9, which is equal to 3. Okay. But if we took the square root of 3 squared, that's the square root of 9 as well, and that's also equal to 3. Okay. So the square root of minus 3 squared is equal to the square root of 3 squared, which is all equal to 3, of course. Okay. Now we have a special operation we use. We call it the absolute value. So we say the absolute value of some real number is equal to the square root of that number squared. Or, yes, that's the way we do it. So this has the effect that it is keeping the sign if a is positive or equal to 0, and it's switching the sign if a is less than or equal to 0, if a is negative or positive or 0. Okay. Thus we can write down 3 is equal to 3 is equal to the absolute value of minus 3, and the absolute value of 5 is equal to the absolute value of minus 5 is equal to 5. Okay. We don't work too much with absolute values in this book, but when you do calculus, you'll be doing it a lot. It's very important in calculus. Let's give an example, though, anyway, of how to work with these absolute values. So over here, trying to save papers and trees, we write x, absolute value of x plus 5 is equal to 2. Okay. So this must mean that x plus 5 is equal to 2, or x plus 5 is equal to minus 2. Either one would work. Okay. So solving for this one, the top one, we subtract 5 from both sides, or we move the 5 over and it becomes negative 5. X becomes negative 3. And for this one, we get x is equal to negative 7. So negative 3 and negative 7 are solutions for x. Okay, so x can be negative 3 or negative 7. All right, so there's two possible values of x that will satisfy this equation. Let's plug it in. So we have minus 3 plus 5 is equal to 2, which is 2. So the absolute value of minus 3 plus 5 is equal to the absolute value of 2, which is just 2. And then we have minus 7, the absolute value of 7, minus 7 plus 5. That's going to be the absolute value of minus 2, which is also equal to 2. So that checks out. Both solutions work. All right. Now, something interesting that people do, and this is kind of cool. It's a cool little trick. The honest truth is we don't use it that much, but some people are pretty, what's the right word? They're very conscientious about this. They don't like to have roots in the denominator. So if you have square root of 1 over the square root of 2, right? Where would you get that? Well, sometimes you just have the square root of 1/2, and you know the square root of 1/2, that's the same as 1/2 to the 1/2 power, which is 1/2, 1 to the 1/2 over 2 to the 1/2, so it's the same as 1 over the square root of 2, okay? So they often write this way instead, square root of 2 over 2, and why do they get away with that? Well, 2 is equal to the square root of 2 times the square root of 2, right? Both of these are positive, so that has to be positive. So if we multiply the top and bottom by the common factor of the square root of 2, so we have 1 over the square root of 2, we're multiplying the top by square root of 2, we're multiplying the bottom by square root of 2, which is totally allowed because those are multiplicative inverses. So in the top we have square root of 2, and we have square root of 2 times square root of 2 is 2. And so that's why we often write it out this way, okay? Now, in general, this isn't really useful, he points out. Sometimes it's useful because it helps us manipulate equations. Sometimes we want to move the denominator down. So we have square root of 2 over 2, and we want to convert that to 1 over square root of 2, right? So from here on out, he's going to give a bunch of examples. And all you have to do is remember that when you have a sum of two numbers multiplied by the difference of those two numbers, that's the same as the difference of the squares, okay? So let's do an example. He has, in the book, he says we have 3 all over 2 plus square root of 5. And we want to get rid of that square root of 5 on the bottom. Okay. So what we're going to do is we're going to multiply this by the opposite. So we're going to multiply by 2 minus the square root of 5. And what that means is we're going to basically take the square of this one and the square of that one and subtract the 2. But in order to multiply by that, we need to multiply it on the top as well as a common factor. And so we have 3 times 2 root of 5. So that's 3 times 2 minus 3 times the square root of 5 all over, and we have 2 plus root of 5 times 2 minus root of 5, so we have 2 squared, which is 4, minus square root of 5 squared, which is 5. So doing some more simplification, we have 6 minus 3 root of 5 all over minus 1, which we can rewrite as minus 6 minus 3 root of 5 all over 1, or we can just write that as minus 6 plus 3 root of 5. Okay? That's what you can do there. Okay. Yeah. All right. Example. Let's do the same thing, but this time we want to move it down to the bottom. So let's use a different color. Let's use a nice blue. I like blue. Blue is nice. Let's start in the middle here just to waste as much paper as possible. So square root of x plus h minus the square root of x all over h. Okay. And we note that x plus h is greater than 0 because we don't know how to do square roots of negatives yet. We need new numbers for that. We have a name for them, and the name is imaginary. It's not because they don't exist. It's because we just need a name for it. Okay, so how do we manipulate this so that the square root signs only occur in the bottom, the denominator? Well, let's multiply the top by the square root of x plus h plus the square root of x. So now we have something minus something and something times something. In order to do that, we have to multiply the denominator by the same things. This over that is equal to 1. Okay, we should probably note that we can't have the square root of x plus h plus the square root of x equal to 0. We can't do that. And then we multiply those two, and we get this squared, so we get x plus h minus the other thing squared. Square root of x times the square root of x, that's just minus x. Okay, all over h times the square root of x plus h plus the square root of x. And here we can see that these two x's cancel, and so we get h over h times the square root of x plus the square root of x. We can factor out the h. Also, h cannot be equal to 0. And then we get finally 1 over the square root of x plus h plus the square root of x. All right? So we call this process, when we're moving the roots from the denominator to the top, we call that rationalizing the denominator. And when we move them down so that we only have we have no roots in the top, we call it rationalizing the numerator. These are useful in practice. They often simplify things, but we don't do it very often until we get to Pythagorean theorem and stuff like that. So hopefully this is somewhat enjoyable to you as a trick that you can show at parties. You can rationalize a numerator or denominator, and you can be popular with all the cool kids who don't know how to do that, and they will probably worship the ground you walk on as you show them the amazing algebra talent that you have. All right, let's talk about homework help. Exercise 1, prove if a is a real number, then a squared is positive. That should be fairly easy. You think if a is positive or a is negative, or if a is, oh, I guess it doesn't work because positive doesn't include 0, does it? Am I wrong? Does positive include 0? No, I don't think it does. Or is it positive? What's the definition of positive he uses in the beginning here? He says positive numbers. If a number is not positive and not 0, then we say this number is negative. We have a positive number represented on a straight line by the numbers unequal to 0 and lying to the right of 0. So if a is positive or a is greater than 0. So this is interesting because, I'll just be quiet. If a is a real number, then a squared is positive. You can't prove that. There is a special number that if you take the square of it, it is not positive. You get to figure it out. All right, if a is positive and b is negative, then ab is negative. That should not be hard. If a is negative and b is negative, then ab is positive. That should not be hard either. Okay. Prove number 2, if a is positive, then a minus 1, a to the minus 1 is positive. That should not be hard. You just have to remember that a times a to the minus 1 is equal to 1. And same thing for the other one. Number 3, number 4, if a and b are positive numbers, then the square root of a over square root of b is equal to the square root of a over b. I kind of did that over here. But see if you can find another way to prove that using the foundational rules that we have. Number 5, that's rationalizing the denominator, which we just did. Number 6, the multiplicative inverse of 2 root plus the root of 3. So let's go ahead, let's go over this one. What he means by multiplicative inverse means that you have some real number a times a to the minus 1 has to give you 1. So in this case, we're taking 2 plus the square root of 3, and we have to multiply this by something and get back 1. Okay, so the question is, what is that number? That's what they're asking. And once you find that number, then prove that it's basically something plus something times the square root of 3. All right? Where C and D are rationals. So C and D are rationals. C, D are rationals. They're in Q, the rational set. 7, same thing. 8, let A be rationals, A and B be rationals. Prove that the multiplicative inverse of A plus B over 2. Yeah, 8 is just a general case of 6 and 7, so you don't have to use numbers anymore. 9, this time do it for root of 3. 10, we have 4 numbers x, y, z, and w that are rationals. Show that a product of these numbers can be expressed in the form of c plus d root of 5, where c and d are rational numbers. Okay, that should be pretty fun. 11, generalize 10 by the square root of a rather than the square root of 5. 11, 12, rationalize the numerator in the following expression. So we just did that. That should be fairly easy for you. Number 13, find all possible numbers x such that the absolute value of x minus 1 equals 2, for instance. A 13 and 14. These are not terribly difficult. You just have 2 equations you have to solve. One where it's positive and one where it's negative, right? And 16, more rationalizing. 16, 15, and 16, 16 is basically 15, but for the denominator. Should be fairly straightforward. Prove that there is no real number x, this is number 17, such that x square root of x minus 1 equals 3 plus the square root of x. Hint, start by squaring both sides. There is no real number x, such that the square root of x minus 1 equals 3 plus the square root of x. Ooh, 17 sounds like a lot of fun. I'm not going to give you too many hints, but yes, that hint to square by both sides is a very good hint. And then you have a regular equation. Okay, but note, remember, when you take 3 plus the square root of x squared, that is definitely not equal to 9 plus x. Okay, you have to use the right formula for that. So don't be tricked. Don't be fooled. If the square root of x minus 1 equals 3 minus the square root of x, prove that x is equal to 25/9. Number 18, fun, fun, fun. 19, determine in each of the following cases whether there exists a real number x, not a rational, a real number x, satisfying the indicated relationship. And if there is, determine this number. Wow. So 17 showed that there is no such real number for that equation. 18 showed that there is, and you can find it. And 19 says, is there or is there not? And if so, find it. Okay, so 17, 18, 19 go together. Finally, for 20, if a and b are two numbers, prove that a, the absolute value of a minus b, is equal to the absolute value of b minus a. And if a and b are two numbers, so we want to prove that the absolute value of a minus b is the same as the absolute value of b minus a. And how would I prove this? Well, I would basically see the relationship between these two things. What is the relationship? Is there some number that you have to multiply? Or is there some number you have to add? How are these two numbers related? If you can figure out the relationship between these two numbers, a minus b and b minus a, then you'll have your answer, basically. All right, next section is powers and roots. We're going to extend what we've learned about powers and roots for rational numbers and integers, and we're going to extend it to the real numbers. Guys, I hope you enjoyed this episode. Have a nice day. Take care, and bye-bye. Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's basic mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.